Alright, this is Mr. Gillum, and today what we're going to learn about is the triangle inequality theorem. The triangle inequality theorem says that the sum of the lengths of any two sides of a triangle is greater than the length of the third side, so in any order. Now, when we talk about triangle, that means we can't have any exterior angle at the same time. So even though there is a triangle there, I'm talking about this little guy. This endpoint of this segment connects with each endpoint of every other segment. Because this endpoint doesn't touch this endpoint, it's not a perfect triangle. The theorem is for perfect triangles. Perfect polygon triangle. So what it's saying is this. If I add, let's just do this. Let's do color coding. AB and BC, it should add up to be more than AC. If I do BC and AC, those lengths added up should be greater than AB, the third missing side. And finally, if I do AB and AC, those side lengths should add up to be more than the length of BC. Alright, so that's what the triangle inequality theorem says. It says any two sides of the triangle will add up to be larger than the last remaining side, the length of the last remaining side. So let's just check a few triangles here. If these segment lengths will connect to make a triangle, then I know that these three inequalities must be true. Segment 2, or sorry, the length of 2 plus the length of 3 should be greater than the length of 4. The length of 2 plus the length of 4 should be greater than the length of 3. And the length of 3 plus the length of 4 should be greater than the length of 2. So I know that 5 is greater than 4, I know that 6 is greater than 3, and I know that 7 is greater than 2. So I know that these could be the possible lengths that make a triangle. So yes, this could make a triangle, perfect triangle, perfect polygon triangle. 1, 2, and 3, however, let's take a look at this one. Draw them in a red color. If these lengths could make a triangle, a perfect triangle that each end of each segment would connect each other, then I know that 1 plus 2 should be greater than 3. I know that 1 plus 3 should be greater than 2. And I know that 2 plus 3 should be greater than 1. Now, 2 plus 3 is 5, which is greater than 1. 1 plus 3 is 4, which is greater than 2. However, 3 is greater than 3 is not a true statement. So I know that these could not be, these three lengths, these segment lengths could not make a perfect polygon triangle. Not a triangle. Alright, and so basically you need to check each combination of the side lengths to make sure that the two side lengths add up to more than the third side length that's not being assessed. Okay, now the fun stuff. If Mrs. Bailey gave Jane 4 pieces of copper tubing measuring 6, 7, 9, and 16 meters, how many different triangles could Jane make? Well, let's take a look here. What we need to do is we need to come up with all the different combinations of triangles. So we could do, oh, this is going to be tricky. We have several different ways we can make a triangle. Now we only need 3 of the 4 to make the triangle. So let's take a look here. We could do 6, 7, and 9. We could do 6, 7, and 16. We could do 6, 9, and 16. Or we could do 6, 7, 9, and 16. Those are the 4 different lengths, or 4 different combinations of lengths that are possible. Now 9, 7, 6, we already have that in 6, 7, 9. So we don't want to repeat it because those are still the same copper lengths. So we wouldn't write it twice. So we just need each of the unique different sets of 3. So I'm going to check here, and I know that 6 plus 7 should be greater than 9. So far, so good. 6 plus 9 should be greater than 7. That works. And finally, 7 plus 9 should be greater than 6. So that's one of the ways that she could do it. She could use these 3 pieces to make a perfect triangle. Or, let's check this one. 6 plus 7 must be greater than 16. Okay, so right away I know that this isn't going to work. So that combination of copper piping is not, or copper tubing is not going to make a perfect triangle. Let's try 6, 9, and 16. 6 plus 9 must be greater than 16. Okay, so right away again, I know that 15 is not greater than 16, so I know that that combination of tubes is not going to make a triangle. And finally, 7 plus 9 must be greater than 16. I know already that that is not the case. Now, of course, I would need to check to see 6 plus 16 is greater than 7, and 7 plus 16 is greater than 6. But as soon as one of them doesn't work, then I know for sure that it can't make a triangle. Okay, so if 2 out of the 3 for your triangle inequality theorem work, that third one is what's keeping it from working, then it's not a triangle. Okay, so that's why I didn't continue on with these two, because the first one that I tried just happened to not, to disqualify it from being a perfect triangle. Okay, so there's only one different way. One way Jane could make a triangle. All right, so a little bit of almost like statistics there, trying to figure out all the different combinations. Our next problem says that the length of two sides of a triangle are 8 and 13. What are the possible lengths of the third side? So let's take a look here, and remember we're using our triangle inequality theorem today. Let's just say that we had a side of 8 and a side of 13, and we didn't know the last side was represented with a variable x. The triangle inequality theorem says that, let's just stick to that for a while, 8 plus 13 must be greater than the side length x. And we also know that, leave a little space there, 8 plus x must be greater than 13. And we also know that 13 plus x must be greater than 8. Now these all must be true. These all must be true to make this triangle. So what we're going to do is I'm just going to find the relationship for x. So I'm going to say 21 is greater than x, or usually we like to graph it if 21 is bigger than x, then x is less than 21. And so what I'm going to do is I'm going to draw a little graph over here to kind of model what my possible solutions are. And I'm going to start here at negative 10, negative 5, 0, 5, 10, 15, 20, and that's fine for now. And so what I'm modeling is I'm going to go ahead and model this x is less than 21. So open dot, all these numbers right here. X could be any of those numbers. However, there's other things that are qualifications of this thanks to the triangle inequality theorem. I would also say that the x must also be, there's more restrictions. X could be greater than 5. So that's also part of my little deal here. I got to make sure that the values are also greater than 5. And finally, if I want to do this guy right here, 13, x could be greater than negative 5. So I got to go down here to negative 5. And so there's my 3 lines of inequalities, or my restriction lines. The only solutions must fit all 3 restrictions. So my solution set is actually going to come in between where all 3 lines meet. So from 5 up to 21. So the only side lengths that I could have are lengths that are greater than 5 and less than 21. All the values bigger than 5 and less than 21. They all have 5, but however, it's not included. They all have 21, however, it's not included. This little segment right here is the only part that all 3 of the restrictions share. So that is those are the only lengths that x could be, the missing side could be. Okay, so any side length in between 5 and 21 will make a triangle. Okay, between what 2 numbers must the measure of the third side fall? So this is the same kind of deal. We're going a little quicker this time, but we need to figure out 9, 15, and we need to know the last side. So we're just going to call them x. We know 9 plus 15 should be bigger than x. we know that 9 plus x should be bigger than 15, and we know 15 plus x should be bigger than 9. So once again, I'm going to go ahead and model each of these. I'm going to say that 24 is bigger than x, or x is less than 24. I'm going to say that if this is one of my inequality properties here, subtraction property of inequality. X could be bigger than 6. And finally, I'm going to say that x is greater than negative 6. So when I model these, let's just go by the same standard we did last time. Let's just take a look here. It looks to me like x is less than 24, so not including 24. X must be greater than 6, and x must be greater than negative 6. So my solution actually is where all three inequalities or restrictions, wherever they have in common. So it looks to me like my x values are x must be bigger than 5. Oh, no, that's a 6, sorry. That's why I should number lines a little more carefully. It should be bigger than 6. This is actually a 6 right here. And it should be less than 24. Not including 24. This open dot says that we can't include it because it's not also, it doesn't share in all three. And this open dot says that we can't include 6. So 6, bigger than 6 and less than 24. All right. Let's just do one more here. I think you get the idea. We don't know what the missing side is here, or where it could be, so we're going to use the inequality triangle theorem, and we're going to say 11 plus 20 is bigger than x, or we could say 11 plus x is bigger than 20, or we could say that 20 plus x is bigger than 11. These are my three restrictions. For sure, the triangle inequality theorem says if it's a triangle, these three statements must be true. So I'm going to say 31 is bigger than x, or x is smaller than 31. X is greater than 9, or x is bigger than negative 9. So instead of, well, yeah, I guess we should model it. Okay, we need the negative 9, so here's negative 10. And we need to make sure our number line goes all the way up to 31. So 25, 30. Ugh, I wish I would have done these a little neater. Okay, so here we go. We have to be smaller than 31. We have to be bigger than 9. And we also have to be bigger than negative 9. So the parts that they share in common are, okay, let's see, it's a 9. From 9 all the way to 31. So I'm going to say that my last value must be between 9 and 31. 9 is less than x is less than 31. Okay, and I'm putting less than, not less than or equal to, because this part, this open dot, makes my restriction not include it. All right, so 9 is less than x is less than 31. And I think you get the idea, so you know what, why don't we practice this one, and I'll see if you can figure out 23 and 14, what its last missing side is for the notes on your own. And that's it for today, the triangle inequality theorem.